I got the bias current blues. Last lecture we looked at some of the issues of bias current. Now let's look at how the bias current of an amplifier impacts the design of your circuit and how it compromises your overall system. From the previous lecture, we discovered we can create a model of an imperfect op-amp by using a perfect op-amp plus current sources, which gives you a model of a real op-amp. We also discovered that for a simple op-amp, we can assume that the bias current into the positive input or the negative input are approximately equal. It's not always the case, but it's a good general rule. And the definition of bias current is the sum of the bias current in the positive input added to the sum of the bias current in the negative input divided by 2 to give us the average. Let's look at some of the issues with bias current. And let's start with a perfect op-amp and in an inverting configuration. If both resistors are identical, then we have the output voltage is precisely the inverse of the input voltage. If we take a low value resistor such as 2 k ohms, that equation still holds true. However, if we increase it to 20 k ohms, you may start seeing a small difference in error at the output voltage compared with the input voltage. It may not be precisely the inverse of the input voltage. And if you increase the resistors even farther to 200 k ohms, then it's almost certain that the output voltage will not be the precise inverse of the input voltage. You've seen an error. In a perfect op-amp, the equation V out equals minus V in is independent of the value of R. However, in a real circuit, you will start seeing errors as the value of R changes. So let's start doing the analysis again. Let's take a generic value R for both the feedback resistors. And let's apply our input bias currents. We have an input bias current IB minus flowing from the inverting terminal and an input bias current IB plus flowing from the non-inverting input terminal. And you should note that in this schematic, the triangle is still a perfect op-amp. We have modelled imperfect op-amps by applying the two bias current sources external to the perfect op-amp. So we have developed an equivalent circuit to represent and model the real situation. So let's see if we can simplify this circuit. Well, the current flowing from the non-inverting terminal is connected from ground to ground. So we can actually neglect that current source because it's not going to change the voltage at this node here because it's defined by the connection to ground. We can also make the assumption that the input voltage comes from a voltage source, so it is not changed by any of the flow of bias current flowing through the circuit. So if that voltage cannot change because it's defined by a rigid voltage source, then the only thing that can change to compensate for the bias current is the output voltage. And the output voltage has to change to force the input voltage to be zero. So if it forces these two nodes to be zero, we can now define the current flowing through the first resistor as the input voltage divided by that resistor, because we know that this node here is a virtual earth and it must be at zero because the other input is at 0 volts. Similarly, we can also calculate out the current flowing through this resistor, which is this current here, minus the current flow that goes down IB minus. So we now have the current flow going through the second resistor, and hence we can calculate that the output voltage is equal to minus Vn plus R times the bias current, because we know the current flowing through here, and hence this end is 0, so we can calculate out the output voltage quite simply. The effect of the bias current adds an error V equal to R times the bias current to to the output. In other words, if the input voltage was, say, 1 volt, the output voltage would be minus 1 volt plus the error due to the bias current. If we now address the same analysis to an inverting amplifier, but this time place gain into the equation, we have the same situation, that we are forcing the negative input to be at 0 volts because the positive input is also connected to 0, and we can do the analysis, and it works out that the output voltage is the classic transfer function plus the bias current times R2. We have an error, and this is an equivalent input error of Vin minus IBR1. In other words, if we were to modify the input voltage, we would have to subtract IB times R1 to get the same equivalent error at the output. This gives rise to an important concept. We can have and we can state errors referred to the output of an amplifier, or we can state them referred to the input of the amplifier. And it depends which way we want to state them in order to make our analysis of the circuit more straightforward. If we talk about the error at the output of the amplifier, it is IB times R2. This part of the equation here is the theoretical result, and this part here is the error result. But equally, we can actually relate that to the input and state it as an error at the input. And in this case, it would be a case of a minus IB times R1. And I encourage you to go and do the analysis to prove to yourselves that these two errors are in fact exactly the same. This allows us to start building Thevenin and Norton equivalent circuits. So if we want to look at the output referred error, this one here, it's the same as having a perfect op-amp in series with an error that is equal to the bias current times R2. It's important to notice a sign here so that for 0 input voltage we would actually get a slightly positive output current. But that is the same as doing the calculation here and having an input referred error. So the same error can be stated as an error of the output voltage, or it could be stated as an error of the input voltage, and it depends how you want to relate it. As an output voltage, you may want to know what is the error appearing there, but you may also say, I know my input is varying, so without any input, what would the error be at the output? So what would the equivalent error be to apply to the input that would give the same error at the output? So there's two different ways of looking at it: output referred or input referred. However, there's a cool fix to remove the effect of bias currents from your circuits. And if we have a circuit in this format here, where we have R and R, if we put a resistor R upon 2 in series with the positive input, any bias current coming down there is going to make a voltage there of IB times R2, R upon 2, and that compensates for the error at the output. But I'm not going to go into detail at that in this lecture, and we're going to analyze this fix for bias current errors in the next lecture. Thank you very much for your time, and I look forward to speaking to you in the next lecture. Goodbye.